Hi everyone. So today we are jumping back into the land of sequences, and we talked about sequences way back in chapter 3. We learned about arithmetic sequences, which were sequences that grow by addition, where you're adding something over and over again. Today we're jumping into what's called a geometric sequence, and geometric sequences are created, instead of through addition, they're created through multiplication. Okay, so let me give you an example of a geometric sequence, and then we'll kind of use that as we establish some formulas down here. But so a geometric sequence might look something like this: 2, 6, 18, 54. I'm using a bad pen. Let's see what the next one would be. 150, I think 162, and so on. Okay. So you'll notice what's happening here is that instead of adding a constant amount, instead of having that constant difference that we had with arithmetic sequences, we are multiplying by something every time. So here we're multiplying by 3, here we're multiplying by 3, and so on. Okay? That's what makes something a geometric sequence, is if there's a pattern of repeated multiplication. So let's remind ourselves what recursive and explicit formulas do. Recursive formulas define a sequence by saying, here's how you get from one term to the next. So in this particular sequence, we would say something like term 1, and I'm using a G because it's a geometric sequence. You could also just use a T for term. We would say term 1 is 2, and then to get to the next term, we're taking the previous term. So to get this term, for example, to get term 3, we're going to take term 2 and multiply by 3. So I'm taking term 2, or previous term, and multiplying by 3. Okay, that's what a recursive formula for one of these sequences would look like. Okay. By the way, just some terminology here to throw at you. This 3 number, the thing that you're multiplying by over and over again, if you remember when we talked about arithmetic sequences, we referred to a constant difference. In a geometric sequence, this number is referred to as a common ratio. That's that thing that you're multiplying by over and over again. And we use the letter R to represent it. So this is an example of a recursive formula that's specific to this sequence that I made up here. If you wanted just sort of a general recursive formula, you're always going to write G1 equals something, because remember, recursive formulas, you always define the first term. And then to get to the next term in a geometric sequence, it's always going to come from taking the previous term and multiplying by the R value. Okay, so this is kind of your generic explicit formula. I'm sorry, recursive formula. That's your generic recursive formula. So now let's think about an explicit formula. And remember, an explicit formula is where I can just plug in whatever term number I want. So if I wanted to suddenly jump down to term 12 down here, the explicit formula would allow me to just plug in a 12 and it would spit out my answer. With a recursive formula, if I wanted term 12, I would have to generate all 12 terms to get to that term number 12. So let's think about this for a second. Let's think about, and I'm going to go smaller than term 12. If this is term 1, and this is term, let's see, this is 1, 2, 3, 4, 5, term 5. Let's think about how I could jump straight from term 1 to term 5. Well, I'm starting at 2, right? And I know that I'm multiplying by 3 repeatedly. So let's see, how do I want to write this? I'm going to write this, I think, down below here. If I'm trying to get to term 5, I'm starting at term 1, which is 2, and I am multiplying by 3 over and over and over again. So I'm multiplying by 3, 1, 2, 3, 4 times. So ask yourself, how do we show repeated multiplication? How am I going to show that I'm multiplying by 3 4 times? Well, we show repeated multiplication with exponents. So I would say term 5 could be found by doing 2 times 3 to the 4th power. And if you check that in a calculator, I don't have a calculator here to show you, but if you do 2 times 3 to the power of 4, we do in fact end up with 162. Okay, I'll just use this little baby calculator here to show you. But so this will get me to my right answer. So let's think about that more generically. If I want to get to any term in this sequence, so instead of term 5 specifically, if I want to get to any term, I would start at term 1, which is 2, and I would multiply by 3 a certain number of times. But let's think about how many times it would take. Why is it that when I wanted term 5, I multiplied 4 times? Or if I wanted term 7, I would multiply 6 times. Or if I wanted term 12, I would multiply 11 times. The reason for that is because you're starting at term 1. So to get from 1 to 5, that's only 4 jumps. Okay, if I wanted to get from term 1 to term 7, that's only 6 jumps. So this exponent up here in the explicit formula is always going to be 1 less than whatever this term number is that you were trying to find. Okay, so if I wanted the explicit formula for this sequence, this is what I would do every single time. To get to term 27, I would go 2 times 3 to the power of 26. So I would do 27 minus 1 and get 26. Let's write that in a more general form because you're going to want that for your homework tonight. Anytime I'm working with a explicit formula, we're going to say that G sub n, and I probably should have used G here instead of T, is term 1 times the R value, because that's really what this 3 is, right? That's the R value, and this is term 1. Okay, so term 1 times R to the power of n minus 1. These two things over here are the formulas that you're going to want to know when you go to try these problems on your own. Okay, again, these are kind of specific to the sequence that I just kind of made up there as an example. Okay, so let's try to put this to use here. This first one is a recursive formula, and it says just give me the first 5 terms. So remember, with a recursive formula, they give you term 1. So my first term is just 4. And then let's think about what this is saying. This is saying to get to the next term, I'm taking previous term and multiplying by 2. This is the important part, that I'm multiplying by 2 every time. So I should just be able to jump through my next couple of terms. So I'm going to multiply by 2, which is 8. Multiply by 2 again, which is 16. Multiply by 2 again is 32. And then one more is 64. I think that's the first 5. Yep, there we go. Now it says let's write an explicit formula. So for an explicit formula, that's where I'm using this setup right here. And I'm going to say to get to any term in this sequence, I'm going to start at term 1, which was 4, and multiply by the R value, which again, I want to point out that the R value is this multiplier. So I'm going to multiply by the 2 n minus 1 times. And let's just put this theory to the test here. So let's suppose I'm looking for this 32, which is term 4. Okay, that means I should be able to plug a 4 in right here and get 32 out as an answer. I'll grab a calculator real quick here. So I would go 4 times 2 to the power of, and again, I'm looking for term 4, so I'm going to go 4 minus 1, or really that's just a 3, and that does spit out 32. Okay, I could test it with, term 6 would be what comes after 64, so we know that would be 128 because it would just double. So if I wanted term 6, I would do the same thing with a 6 right here. So 6 minus 1, I know that's hard to see, you'll see it in a minute. And that comes out to be 128, which is what would come after the 64. So there's your explicit formula for a geometric sequence. Okay, next one's asking you a similar question, except it's starting you with an explicit formula. Remember, with an explicit formula, when you want term 1, you're going to plug in a 1. When you want term 2, you're going to plug in a 2. So, and really, just looking at this formula, you should be able to identify that this is term 1. But if you weren't sure about that, we could say, okay, term 1 is 6 times 0.5 times to the power of 1 minus 1. Term 2 would be 6 times 0.5 to the power of 2 minus 1. I'm going to leave myself a little space to actually evaluate those. Term 3 is 6 times 0.5 to the power of 3 minus 1. Term 4, 6 times 0.5, power of 4 minus 1. Term 5. Now, would I actually expect you to write all of this out every single time? I'm kind of hoping you won't have to. Actually, once we start evaluating these, I want you to see that there's a pattern to them where you should be able to figure it out and just generate the rest of the terms without having to recalculate every time. But I want you to see that that's how an explicit formula is supposed to work. For an explicit formula, if I want term number 4, I drop a 4 in for n. Okay? And so if you want the first 5 terms, you just plug in the numbers 1 through 5. So let's try this. Like I said, we should know what this is at least going to start out as. So 6 times 0.5 to the power of 1 minus 1 should give me 6. And again, I knew that because the way this formula is written, we always start with G1 right here. So this is 6. So now I'm going to do the exact same thing with 2 minus 1, okay, which is 3. Okay, let's try it with 3 minus 1. And I end up with 1.5. So take a look at what's happening. We went from 6 to 3 to 1.5. Can you get an impression of what's happening here? I mean, really what's happening is we're cutting in half every time. And we knew that because our R value here is 0.5. That's what we're doing, is we're multiplying by 0.5 each time. So I would guess that my next term is going to be 0.75 because that's half of 1.5. And then my term 5 should be half of that, which is 0.375. Okay? But if you didn't know that, or if you didn't catch that, just keep doing what we were doing. So I could go to the power of 4 minus 1. I could go to the power of 5 minus 1. And there's my 5 terms. Okay? Okay, so now let's write a recursive formula. Remember, recursive formula, we always start out by identifying G1. We know G1 from here. We also know G1 from here. Okay, G1 is given to us in a couple of different ways. So G1 is 6. And then we're going to say, to get to my next term, we're always taking the previous term and multiplying by the R value, which is 0.5. You may also see it written, probably I technically should be writing it this way, but you'll also see it written with the 0.5 in front of the G sub n minus 1, kind of how this one is written with the 2 in front up here. Don't let that throw you off, okay? Okay, I think one more example here. So this is an interesting one to talk about. So a ball is dropped from a height of 5 meters. So this initial height here, this is 5 meters, and it bounces up to 90% of its previous height on each subsequent bounce. So this one's 5. So the height of this one is 90% of 5. So I'm going to, in my calculator, I'm going to do 0.9 times 5, and I'm going to find that this bounce is 4.5. Okay. Let's just do one more of these. So I'm going to take this thing and I'm going to multiply by 0.9, and this next one would be 4.05 for a height. And I could keep going. I could multiply by 0.9 again, and that would give me this one, and 0.9 again, and that would give me this one. I want to point out this wording right here. Let h sub n represent the height of the ball after the nth bounce. Okay, so just to clarify, here's the first bounce. This is bounce number 1. So the height after the first bounce would be this 4.5. That means that this is h1. And this is H2, okay? Because this is after the second bounce. Just the way that's worded, that's how I'm applying that to this picture. So what does that mean about this 5? Okay, this 5 can be kind of confusing for people. This is before bounce number 1. This is technically like H0. Okay, this particular sequence has a term 0 in it, and that should make sense to you because that's also your y-intercept if we're thinking about this as a graph, and the y-intercept is always when x is equal to 0. Okay, So here's where this is going to mess us up a little bit. When we go to write our explicit formula, if you are the type of person who is just super committed to memorizing a formula and using it the same way every time, our formula should look like this. H sub n equals H1 times R to the power of n minus 1. That's that formula that you learned on the previous page. So if you are, committed to that, this is what your answer might look like. You would say H sub n equals H1, which is this number, the 4.5, times your R value, which is the 0.9, okay, to the power of n minus 1. So this answer would be perfectly fine with me, okay? But some of you, I'm hoping, are looking at this and saying, well, it's kind of dumb to use this number when we have this number that we started with, right? So you could also write a formula that looks like this. H sub n equals, we're starting at 5, and we're multiplying by 0.9, but let's think about now how many times we're multiplying by 0.9. So if I'm starting at term 0, and let's say I want to get to, term 5. When I started at term 1, that would be 4 bounces away. That would be 4 steps. So from term 1 to term 5, you would multiply by 0.9 1, 2, 3, 4 times. But if I'm starting at this one, if I'm starting at term 0, to get from here to term 5, that's going to be 5 jumps. Okay? So my exponent would no longer be an n minus 1. It would just be an n. So you can use term 0 as your initial value, but in your exponent then you would only have an n instead of an n minus 1. Because when you're starting at term 0, to get to whatever term you want, that's the number of times you're going to multiply by your R value. Okay? So this answer would also be correct. These two things are equivalent to each other. So to find the height of the ball after the 10th bounce, you could do this with either one of those formulas. We're going to test it with both and make sure they come out the same. So if I want H10, I could do 4.5 times 0.9 to the power of 10 minus 1. Or I could do my initial value of 5 times 0.9 and then just go to the power of 10 instead of doing the 10 minus 1. Let's check both of these. So 4.5, whoops, you can't see that. 4.5 times 0.9 to the power of 10 minus 1, which is really just 9. Or we could do 5 times 0.9 to the power of 10. Either way, we're going to get that same value. Okay, so either way, we're going to get that H10 equals 1.74. Okay, so this is another situation, and we talked about this when we did arithmetic sequences as well. You have to be really careful about whether what you're given in the problem is term 1 or term 0, because sometimes it will be one thing and sometimes it will be another. And so you really just have to pay attention to the wording of the problem to decide if the number that you're given should be considered to be term 1 or term 0. Okay, that's it for this lesson on geometric sequences. We will talk about it in class when I see you next time after you've attempted the homework.